All right. Morning, everybody. I hope, well, I know in many cases, a number of you have hit the ground running on your circuits. I know that from office hours and email questions and so forth. Want to start off by asking if anybody has any conceptual questions about the Chapter 1 circuits we're working on, starting with NAND, doing AND, or not, the multiplexer, the demultiplexer, any of that stuff. Any questions about any of that? Yeah, Andrew.
I just have a question about the testing thing.
Yeah.
When it says comparison successful, that means that it works perfectly.
Right. So for each chip, it has this test script. And these chips are sufficiently simple that the test scripts are exhaustive. So it's really two different issues, right? And I think you were kind of hinting at this. All tests completed successfully can really only mean that for some finite number of tests that it ran through in a short period of time, it did the right things. In this case, with these very simple circuits, it also means they have been tested exhaustively with all possible combinations of inputs. That won't always be the case as we continue to work on these circuits. That is, we're going to start dealing with circuits that aren't really being tested for all possible inputs. But the tests will generally have been crafted cleverly enough that almost any likely error has been hit. So it's partly that and partly a matter of rigorously testing the subcomponents. So for example, think about AND16. So AND16 is really just 16 AND gates, right? So if you know the basic AND gate is functional, you have 16 of them, you aren't going to try all possible inputs, right? So let's talk about why you're not going to try all possible inputs. If we're thinking about a gate like AND16, it's got a 16-bit A input and a 16-bit B input. So that's 32 total bits of input. So the total number of possible distinct inputs is this. Now, this value by itself, 2 to the 32nd, might not be immediately meaningful unless I clarify that this is about 4 billion. So nobody has the time or energy to conceivably enumerate 4 billion test cases. Granted, one could, in principle, write a program that generated the test cases, but we're still talking quite a lot of time to do the test, right? Especially because, of course, we have to have a way of specifying what the outputs are supposed to be. So instead, they come up with a suite of tests that, in some sense, exercises every bit. So what kinds of common errors am I referring to here? Well, it's pretty easy to imagine an AND16 where you do something silly like the first line ANDs bit 0A, bit 0B, and puts it to output 0. And the second line does bit 0 of A, bit 1 of B, and sticks it on bit 1 of the output. Well, that's clearly going to be a disaster. And it's a very easy error to make. And so there are going to be test cases that would be triggered by something like that without being exhaustive. So the short answer is, when you run these tests on these circuits, if it says all tests completed successfully, yeah, move on. The long answer is, for simple circuits, it is in fact an exhaustive test that has proven it correct. For more complex circuits, it's not, but it's pretty good, and you should have a high amount of confidence in it. Good. Good question. Other questions so far about this first round? Okay, good. So what we're going to do now is we're going to start looking at Chapter 2. And Chapter 2 is all about building circuits that do math. And so to understand these and to think about these, we're going to actually do some math ahead of time. before I get started on this, I do want to go over our current timetable in terms of the various projects you're working on. So if I scroll over here. So on Tuesday, we talked about Boolean logic. Project 1 was assigned. Project 1 is due tomorrow night. I should have I should be in my office most of the day tomorrow. I should have a lot of appointments available. So you need help with it, please book appointments or even just stop on by. There exist several of you that were successful in both, even just yesterday. So don't hesitate to come by to get some help, okay? Then, like I said, we're going over this arithmetic today. This second assignment will be due on Wednesday. So the material I'm going over today is for project 2, due on Wednesday, okay? And we might do a little bit more of this on Tuesday, but the main focus on Tuesday is going to be the chapter 3 material, sequential logic. And what we're going to be exploring there is how we build circuits that have memory, that retain things. So something that's interesting about 1 and 2, chapters 1 and 2, is the fact that all of these circuits we're currently building are memoryless. That is, you put electricity into them, they spit values out, but they don't have any means of retaining information over time. In chapter 3, we're going to study how that process works, how we can build circuits that retain memory over time. Again, just based on the NAND gate. So anyway, we'll get there when we get there. Today then, before we really get into how the circuits produce arithmetic, we're going to take some time to explore how base 2 arithmetic works. Understanding that thoroughly is important for grasping why these circuits get designed the way that they do. So, so let's start off like this. Why base 2? And we talked about this a little bit last time, but I really want to emphasize it today. The reason we go with base 2 is because of the physical convenience of distinguishing lots of charge versus little charge. That is, if you can imagine different levels of current coming into a circuit, so we could envision there's kind of a low level down here, a high level up here, and then we've got some kind of a cutoff or a threshold here in the middle. So digital circuits are engineered so that this gap is wide enough that this cutoff in the middle reliably distinguishes the low versus the high. So that's an easily achievable physical state. That then enables us by convention to say low is 0 and high is 1. In principle, right, we could say low is 1 and high is 0, and it really wouldn't matter as long as we're internally consistent about our convention. Okay, so in a sense, this is lower level than we actually go in this course, but I think it's useful to know that this is the physical underpinning of what we're able to do in building a computer. Everybody with me so far? Okay, so that's why base 2. So now, how does it work, right? So the idea of numbers in any base is that you've got this notion of place value and digits. So base 10, which you're accustomed to by convention since your earliest arithmetic years in school, works something along the following lines, right? So you've got the 10 to the 0 column, the 10 to the 1 column, the 10 to the 2 column, and so forth. And that can continue indefinitely. Now, I wrote this in terms of 10 to some power. Odds are that's not exactly how it was presented to you in first grade when you first saw this, right? Instead, they talked about, well, there's the ones place, the tens place, the hundreds place, and so forth. But all that really is, a little more abstractly, is to say, this is the 10 to the 0 place. This is the 10 to the first place. This is the 10 to the second place. And the reason it's valuable to think of in this way is this gives us a manner of thinking about an arbitrary base for a numerical system just by substituting that base in for 10 in these place value columns. Before we get to base 2, I'm actually going to show you another base that's extremely frequently used in low-level computing. And that is base 16. So what does that wind up looking like? Well, you've got the 16 to the 0 column. You got the 16 to the 1, 16 to the 2, and so forth. But of course, now it's like, well, wait a minute, what are we going to do? We've got digits 0 through 9. We need 6 more digits. So aficionados of base 16 use the letters A through F for those digits. So for instance, you can have a number along the following lines. You could have 2FC. And what would that be? Well, C is 12. So you have 12 times 16 to the 0. F is 15, so you've got 15 times 16 to the first. And 2, of course, is just 2. Now, what are these values? Well, 12 times 16 to the 0 happens to be, 12. 15 times 16 is 240. And 2 times 16 squared is going to be 512. And so 2FC hex is 764 base 10. Before we get to base 2, I'm going to mention a major reason why hexadecimal is used is that each hexadecimal digit can correspond to 4 bits, to 4 ones and zeros. And so often when working at the machine level, it's a convenience to use hexadecimal because you can just use a lot less space to write out a bit string. So you'll see it pop up from time to time. So base 2 then. When we're thinking about base 2, it's the same basic idea. Of course, you wind up using a lot more columns. So you have 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, and so forth, right? Now, more conventionally, we might say, well, we've got the 1's place, the 2's place, the 4's place, the 8's place, the 16's, and so forth. Because it's base 2, you only need 2 distinct digits, 0 and 1, which we derived earlier from our notion of a circuit with a threshold, okay? So, you just fill in values corresponding to whatever you're doing, and that's your binary number. This has a lot of distinctive properties when it comes to arithmetic. It's the logical outworking of the way you've always done arithmetic, but good grief, is it going to look weird? So here we go. Let's say I want to add 2 binary numbers. So I'm going to add something like 1011 plus 0111. Okay? So I start my add. Oh, this will do for now. Okay. 1 plus 1. Well, I have to write a 0 and carry a 1. 1 plus 1 plus 1. Well, that's going to be a 1 and carry a 1. Then 1 plus 1 is going to be 0, carry a 1. And then 1 plus 1 is going to be 0, carry a 1. Let's see what this looked like in base 10 terms. So I've got a 1, a 2, and an 8. So that number was actually 11. Here I've got a 1, a 2, and a 4. That number was actually 7. And when I add them, I get 18. Down here, I've got a 0 in the 1's place, a 1 in the 2's, 0s in the 4's and the 8's, and a 1 in the 16. So I've got 16 plus 2, 18. So they agree with each other in some form. Now, something really tricky that we encounter when doing binary arithmetic at this low machine level is the issue of overflow. So what do I mean by this? Here I added two 4-digit binary numbers. In any physical computer, there's going to be a basic resolution of binary number that's employed. For example, like I mentioned on Tuesday, I'm going to be doing a lot of nostalgia in this class. Okay. So if we think back to the great year 1982, in which I got, at the age of 10, my Commodore 64, that CPU performed all of its arithmetic on 8-bit values. We'll think about the implications of that in a moment. Not too long thereafter came the first IBM personal computers. Those were 16-bit width. By about the late 80s or thereabouts, we started having 32-bit machines. And then around the turn of the century, turn of the millennium, take your pick, we started getting 64-bit machines. And at this point, just about any commercially sold machine is going to be 64-bit. What does this imply? What it implies is, if I've got an 8-bit machine, and I'm performing arithmetic, if I'm adding two binary values, and I run out of space like I did here, then on one level, I'm kind of out of luck, right? So this is an important property of any system of binary arithmetic, is that you've got this bounded number of digits because of hardware, right? Which means there is a limited range of values you can actually perform arithmetic upon. It's bounded. And if you go outside of those bounds, too bad. Now, you might be thinking, well, there's got to be a way to deal with this. After all, back when I coded in Python, I could add arbitrarily long numbers and they would get all huge and stuff. And that's true, but it's not working at the machine level to do that. So a language like Python, for example, has integers represented not as single machine words, but as arrays. And so in practice, something that arithmetic hardware is also going to do is it's not really going to throw this away. It's going to hang on to it as what's called a carry bit. And then you can reuse that bit when adding the next block of bits for some larger number. So, you know, my poor Commodore 64 had this 8-bit word size. So if I have 8 bits, how many distinct integer values do I have? It's not a lot. Anybody ever play that doubling? I forget what the game is called, this little game that's like you keep doubling things. What's it called? Yeah. This is an exercise in 2048. So how many distinct values do we have with 8 bits? Pretend you're playing 2048. Very close. It's 256. Yeah, it's 256. So yeah, my poor Commodore 64, if I was programming in machine language, I had at most 256 distinct integer values. Pretty easy to overflow. Yes?
Is there a formula to get that number? Like, why is it 256?
Oh, it's 2 to the 8th power, because for each of 8 possible positions, I could have a 0 or a 1. Yeah, so with 2 possibilities for 8 positions, 2 to the 8th, 256. Yeah, great question. Thanks, Innocent. Okay, so 16 bits. So this turns out to be 65,536. So you go from 8 to 16 bits, right? So this is, of course, 2 to the 16th. And it's like, that's pretty good. I've got some elbow room here. I'm feeling all right about that. But that overflows pretty easily too, right? Could somebody think of some fairly common kind of program you would write that would overflow 2 to the 16? Just some common businessy thing that might overflow that. Anywhere you would use an int where 2 to the 16 just isn't big enough. Yeah.
So I know that in Java, there is a limit to what a regular int can do. They need to use like a big integer. I don't know if that's what we're going.
We'll get there in just a second, yeah. But in a more elementary way, what's some common business code you might write where this just isn't big enough a number to represent it?
The number of population in an area.
Anybody know the population of Conway, Arkansas?
68,000.
There we go, bam. If we were to record the number of people in Conway, Arkansas, we have beaten 16 bits. Yeah, it's a great example, right? Certainly anything with money could easily be overwhelmed here. Total sales, payroll, what have you. So then we go to 32-bit. And so 32-bit, and Innocent was referring to this, this is actually what an int in Java is. So if you're programming in Java and you exceed 32 bits in your arithmetic, it will actually overflow right there in your high-level language. And the reason comes right back down to the phenomenon we saw right here with 4 bits. Now, I think for a long time, people were like, yeah, 32 bits, that's plenty, right? Because that gets us 4 billion. So it'll be something that overwhelms 4 billion. Yeah, that's not hard, right? Yeah. Global population. Bam! It's out of there. So, people started migrating to 64-bit. 64-bit is big. Innocent was making reference to, in Java, if int isn't really satisfactory, there is actually in Java another type called long, which is a 64-bit value. But there's also a class called BigInt, which does what Python does and basically builds out an array of machine words and goes from there. The funny thing about Java, right, is it's got all these int types. So Java actually has a separate int type for each of these levels. That's a byte, that's a short, that's an int, and that's a long. So in the 90s, 8-bit machines were pretty close to extinct. There were still some 16s running around, and 32 and 64-bit. So back then, using something like a short or even an int was a way to be conservative with memory. Now, since everything's 64-bit at the machine level, it's like, sure, you can use a short or an int or whatever in Java, and then there are just going to be 32 zeros on the end that it's just sort of sitting on. Because it's a lot more efficient to just let the CPU do everything at the machine level than to try to compact everything and then have to pull them apart and so forth. Plus, memory's gotten ridiculously cheap. My Commodore 64 had 64 kilobytes of RAM. The machine we designed this semester is going to be more like a Commodore 64 than something you actually purchase these days. But yeah. we're actually going to develop a 16-bit CPU, which is why we've got AND 16 and OR 16 and MUX 16 and so forth. We're going to be operating on 16-bit arithmetic. But still, this is a thing, right? Overflow and so forth. But it also has some extremely interesting, surprisingly useful properties. Let me show you what I mean. I showed you addition. Really, really tricky. Subtraction. Here's what makes subtraction subtle, right? If we have subtraction, we have to have a meaningful way to talk about negative numbers, right? Once you've got subtraction in there, yeah, some Yahoo's going to come along and subtract 1 minus 4 and expect the machine to behave, because that's just what people do, right? So what are we going to do about this? Well, there are several approaches one could imagine. Here's one approach. Let's say I want to represent a value like -3, okay? So as we know, +3 in 4 bits is this, 0, 0, 1, 1. There's a 1 here and a 2 there. 1 plus 2, 3. So here's one approach we might take. We could say, you know, this leftmost bit, we're going to make that the sign bit. So if there's a 0 there, it's positive. If there's a 1 there, it's negative. And so then we could say -3 is 1, 0, 1, 1. And that's kind of okay. We're not going to really get into details in it in this course, but floating point representations actually use this kind of a scheme. But it's got a bit of a disadvantage. Let me show you what I mean. If 0 is this, what is that?
Zero.
Is it? What would you call that? But this is the sign bit. I think Andre's about right. You know, this is -0 and this is +0. So this is a problem, right? What makes this a problem? Why is this not a desirable feature?
Zero can't be negative or positive. Zero.
It really is just 0. So arithmetically, conceptually, it doesn't really make any sense. There's an intensely practical reason on top of this, though, as to why this is not a desirable property. Well, it's really this. 0 is then not equal to itself, right? +0 and -0 are distinct values. So if I have a circuit that's intended to compare them for equality, they wind up not being equal to each other. So this is sort of like a basic way to think about it. It's intuitive. It's what kind of got done as a first crack at it. This is not how negative numbers are represented in a modern machine. And that's what I'm going to go over next. We actually have a scheme that not only ensures that 0 is always 0, but also allows us to implement subtraction strictly using addition. So if we can add, we can also subtract. Here's what I mean. Foundational idea is this. If I have 0, I need to have a way of negating it so that I get a 0 out when I negate. So here's the negating scheme that we're going to use. It has 2 steps. The first step is to apply the NOT circuit. The second step is to add 1. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. Plus 1 is 0, carry a 1, and too bad. This scheme is known as 2's complement. using the not to invert all the bits is complementing. And the 2's is a reference to doing this in base 2 with the adding the 1 to kind of move everything along. So this winds up having some amazing properties. Let me show you what I mean. Let's take the number 1. We're going to do 2's complement on the number 1 to get -1. So we get 1, 1, 1, 0. We add 1. And so -1 turns out to be 1, 1, 1, 1. Now, how is this beneficial? Check it out. Let's say I want to do 2 minus 1. So I have this 2, and I want to subtract 1, or in other words, add -1. 0 plus 1 is 1. 1 plus 1 is 0, carry a 1. Plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. And so it turns out 2 plus -1, 2 minus 1 is +1. So the 2's complementing scheme in combination with overflow and throwing away the overflow bit allows us to implement subtraction straight away using the exact same circuit as addition, provided we have a means of performing a 2's complement operation. And if we can add 1 and we have a NOT gate, we can perform 2's complement. So this is a pretty powerful idea, because if we have addition and subtraction implemented at the machine level, we can then build on those to create any other arithmetic operation we want over the integers, right? If I can add and I can subtract, I can totally multiply, right, by using a loop. And likewise, I can divide by using a loop. So ultimately in this course, actually in chapter 12, we're going to implement multiplication and division in software. Now, on a modern CPU, multiplication and division are usually implemented in hardware, but they're fairly complicated to do. And so we're going to keep the circuit as simple as possible, recognizing this gives us everything we need. So that then is kind of a basic introduction to binary arithmetic. Any questions so far? Yeah, Innocent.
I like this process of taking a binary number and adding 2 complements of it and adding 1.
Mm-hmm.
But my question is, it looks like the number that you get is another binary number.
Yep, absolutely.
Even though it's still called a negative of the number we had before.
That's right.
How do you distinguish them?
You just decide how you're interpreting the bits. So, I mean, this is an outstanding question. This could be 15 or it could be -1, right?
Yeah.
And so ultimately, whatever software you write just needs to make some kind of a command decision about the interpretation. You know, there's nothing, and this is a really deep and important point. These circuits, this hardware, has no intrinsic meaning, right? All we've done is just wire a bunch of stuff and let electrons flow. Any meaning is meaning that we impose on the system, that we interpret from the system. It's just hard to see this because we're so used to using these things, right? But if we think about the screen display, and we're going to be thinking about it a lot in this course, actually. It's really just, if you think about the monochrome aspect, the black and white aspect, each cell is either like a white indicating a 0 in memory or a black indicating a 1, or vice versa. It doesn't really matter, right? So all the software you design is based on the premise that somebody looking at it is going to interpret the information in that way. In a sense, any computation a computer does is only meaningful to the degree to which somebody observing the computation attaches a meaning to it. And likewise, the programmer has to impart a meaning. So the programmer and the user have to agree on the meaning of what gets inputted and what gets displayed. And that's how the meaning gets carried forward. So coming back to this, the programmer has to intend for this to mean something negative. The beauty of this scheme is that the computer circuit is just doing the same robotic addition regardless. Having done that, we then interpret that result just depending on whatever it is we're trying to do. It's a great question. Now, I have to admit, 2's complement is not perfect. It does have a flaw, and that flaw is this. This -0 value kind of comes to haunt us in a different form. So let's imagine I take this value and I negate it. So I go 0, 1, 1, 1, plus 1, and 1 plus 1 is 0, carry a 1, 1 plus 1 is 0, carry a 1, 1 plus 1 is 0, carry a 1, 1 plus 0 is 0. So if I negate 1, 0, 0, 0, I get that same value back. It's kind of awkward. We usually just try to not operate too close to that part of the range. In all seriousness, right, if I talk about 8-bit and I'm talking 2's complement, my actual numerical range, right, is going to be -128 to 127. So this value in base 4 here is -8. And it turns out if you have your little extreme negative and you invert it, well, it's still that. Just know that. And be really, really careful when you negate minimum integer values in any programming language that's using machine words. Just wanted you to know it was there. It works fine for addition and the like, right? So if I add, say, 1001 plus 1, I'm going to get 1010, which if I do my 2's complement to find out what it's the inverse of, right, I get 0, 1, 0, 1 plus 1, which is then 0, 1, 1, 0. In other words, that's 6. So this was, no, wait a minute. Something not right. Is that -8? Oh, I meant to do this. Sorry. Let me fix the problem. Okay, so then that's 0, and that's a, all right. Time to switch to the eraser. Really?
Yeah.
All right. Reboot. Let's do that again. Okay. So if I got my -8 and I add 1, I get 1001. If I perform 2's complement, I get that plus 1, which is, oh, forgot that part. 0, 1, 1, 1. So that's 7. So if I have my -8 plus 1, I get -7. So it works arithmetically. It's just not real good for inverting. And to be sure, there's really no meaningful solution here. What we would ideally want, right, would be some range of values that's an odd number of values. So we've got the same number of negatives, positives, and then we have a 0 representation. But if we're dealing with binary, that is mathematically impossible to achieve. You know, you have to have an even number of distinct values. So you then get to decide, do you have 0 twice, or do you have this like extra negative number on the end? And the consensus is we'll live with the extra negative number on the end. So there's that. Cool. Any questions? Any questions about this before we start thinking about this in circuit terms? Yes.
I think it told us to be careful with the -8 right there, but
Yeah.
still not see how problematic it can be. Like I'm trying to understand what.
Oh, it's just that if I try to calculate -8, I get -8 instead of positive 8 because positive 8 is not representable.
Oh, okay.
That's the problem.
I see.
Yeah. But there's really no avoiding it. Like, you have to have some kind of representable value that behaves weirdly. There's just no escaping it. So it's sort of a public awareness campaign of some of the limitations of this sort of thing. Cool. Any other questions before we start thinking about this in circuit terms? Okay, so we're going to start thinking about how we develop circuits to do math. The bottom line, most fundamental circuit we're going to develop here is called a half adder. You will, of course, be building the circuit itself, but what I'm going to do here is derive the truth table and talk through how this truth table will enable us to do meaningful arithmetic calculations. So, the goal of a half adder is to add two one-digit binary numbers. So the half adder its addends are only 1 bit wide. That means it's reasonably meaningful to imagine the truth table. So let's imagine what this truth table is going to look like. My addends are A and B. And as everything we've looked at so far, we're going to examine all possible combinations. So A can be 0, A can be 1, B can be 0, B can be 1. This gives us 4 possibilities. First thing we're going to think about then is the sum of the bits. So what's 0 plus 0? Yeah. What's 0 plus 1? What's 1 plus 0? What's 1 plus 1? Trick questions too. Well, anyway, as a 1-bit output, right, 1 plus 1 is 0. But boy, is this unsatisfying. Not just unsatisfying aesthetically, unsatisfying on the level of, yeah, adding 1 bit is fine, but at some point, I want to use this as part of something that adds bigger numbers, right? So it's not really satisfactory to say 0 plus 0 and 1 plus 1 are the same thing. So what I need another output, right? So what do you all want to do conceptually with this other output? What should it be? What might we call this other output?
Maybe
What's that?
maybe a 1 1 or something.
Okay. What were you going to say, Andrew?
Output 2.
We can call it output 2. I mean, it's a name, but conceptually, what is it? It's the overflow, right? We want to explicitly track the overflow. The traditional name for this overflow is to call it the carry bit. So let's work out what our carry bit is for each of these situations. If I add 0 plus 0, what's my carry? 0. 0 plus 1, what's my carry? 0. 1 plus 0, what's my carry? 1 plus 1, what's my carry? Now we're getting somewhere, right? So this is good because each of these 4 combinations results in a distinctive 2-bit output pattern. One way we can conceptualize this is to say that a circuit adding 2 1-bit digit values actually has a 2-digit output, right? So 0 plus 0 is 0 if we read right to left. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is, in fact, 2, right? You can think of this as being the 2's place, and this as being the 1's place. And so we've got something now, this truth table represents a circuit that gives us a complete, consistent, coherent idea of adding two 1-bit numbers. So this is great, right? We can actually represent addition with a truth table. And if we can represent addition with a truth table, it means we can implement addition with circuits, which means computers are possible. Yes, what a relief. So now let's try to imagine maybe some practical implications of this, right? Let's imagine I'm trying to construct a circuit then that will ultimately be able to add 2-digit numbers. So I want to be able to add something like 1, 0 plus 0, 1. Well, with this particular combination of numbers, I could imagine having 2 half adders, and it would do the job, right? So this is kind of analogous to like the AND 16s and the OR 16s and so forth. You can imagine having 16 half adders, right? And so here my half adder says, oh, 0 plus 1, that's 1. 1 plus 0, that's 1. Hey, life is good. 2 plus 1 is 3. But of course, it's not as simple as that, right? What am I sort of hand-waving wildly over? The overflow, right? See, if I want to add something seemingly innocuous, right, like even 0, 1 plus 0, 1, if I'm only using my half adders and I'm only representing the sums in the output, then 1 plus 1 turns out to be 0. That's not good. So what we need is to observe, for that rightmost digit, the half adder is okay. But for all the other digits, what we need is a way to incorporate this carry value from the previous computation and allow that carry value somehow to propagate leftward as we complete the addition process. Everybody with me there? Cool. So to that end, and maybe the name was suggestive, right? We created the half adder. Now we're going to need to think about the full adder. So let's work out a truth table for a full adder. So the full adder is going to be distinguished from the half adder in the following way. Just as with the half adder, the full adder has A and B inputs. But the full adder is also going to need a third input, which we're creatively going to call C. Why? Well, it's the thing after A and B, but also it feels like, oh yeah, the carry from last time, right? So we have A, B, and C, and then we're still going to have a sum, and we still need to have a carry, that is the carry out as a result of the calculation. So, whoops, holy, what? Okay, me and touch screen need to talk. All right, there. There we go. So the half adder was a 2-input circuit. The full adder is a 3-input circuit. To consider all possible inputs, then, we need 8 rows to represent all possible combinations of these 3 input values. So we're going to go ahead and sketch those out, and I'm going to kind of put a curvy line in the middle just so I don't totally lose track, because it's really easy for this to get messy. So initially we'll consider A of all 4 zeros. B will go 0, 0, 1, 1, and C will go 0, 1, 0, 1. Now I'm going to copy B and C down here, 0, 1, 0, 1, 0, 0, 1, 1. And now A is all ones down here. So the full adder has 3 1-bit inputs and a 2-bit output. So let's walk through the inputs. For each row, we're going to derive what makes sense for representing addition. 3 zeros. What's my sum? What's my carry?
0.
Yeah. 0, 0, 1. What's my sum? What's my carry? 0, 1, 0. 1 and 0, 1, 1. What's my sum? 0. And what's my carry? So notice that at this point, all we've really done is reproduce the half adder. Why is that? It's because there was never really a meaningful third input. So that's okay. That's okay. So now things get a little more interesting. I have 1, 0, 0. What's my sum? And what's my carry? I have 1, 0, 1. What's my sum? And what's my carry? 1, 1, 0. What's my sum? And what's my carry? 1, 1, 1. What's my sum? And what's my carry?
1.
Hey, this is pretty cool, right? So now we've got this full adder circuit specified. And the full adder says, given 3 1-bit inputs, I can fully represent the outcome in a 2-bit output. And that makes sense intuitively, right? Because if you've got up to 3 ones, the maximum value you're going to represent is 3, which in binary is 1, 1. So we actually have a fully exhaustive specification of the results of our arithmetic. Right there. So it won't be giving away the store, so to speak, to say that ultimately when you implement your add 16 circuit, you're going to have a half adder to kick things off, and then 15 happy full adders, grabbing the carry from the previous and moving it forward. And then the last half adder, full adder is just going to send its carry to the wind. Now, it's not all that uncommon for a practical add 16 to actually have its own carry output bit. For this class, it's just a tiny increment of complexity that we're just not going to deal with. It's just in the keeping things simple idea of understanding the essence of putting the computer together. But in any practical computer, there will be a carry out for something like add 16. Because then what that lets you do is really cool stuff like you add 16 the low order 16 bits, and then you add 16 the next ones just using that carry input into your add 16 or whatever. So it does create some possibilities there. But for our assignment, that's really all you're going to need to do is discard the final carry bit. So that's the full adder. It's a fairly cool circuit, actually. It's neat stuff. I think you're going to have fun putting it together, fun building it. So if you've got a half adder, and if you've got a full adder, at that point, you're able to do the add 16 just by using lots of them really carefully. So the final aspect of the Chapter 2 project is something that's pretty elaborate and has a lot of potential to be confusing, but is also straightforward in its own way. Whoops. And that last little business is called the ALU. We're going to spend the next 20 minutes or so talking about the ALU. So ALU stands for Arithmetic Logic Unit. The ALU is the computational heart of any CPU. So the ALU represents all of the calculations that can be performed by the CPU. It's all in there. So when we say arithmetic logic, what we mean is all arithmetic possibilities are in the ALU. All logical possibilities are in the ALU. And it's a unit because they're unified. There we go. Anyway. So the ALU is in charge of all math on the CPU. In a way, we can think of a CPU as being an ALU plus memory. If you have an ALU and you have a way to remember previous calculations, you have a CPU. That's really all it is. So let's go over the ALU design for this specific chip. What's important about this ALU design is that its inputs are sufficient to do any integer arithmetic calculation and every possible logical calculation. It's not going to look like it. It's going to look super primitive, but it is actually enough. And we'll talk a bit about how it's enough today, and if we run out of time a bit on Tuesday, whenever it is we have class again. Anyway, so what are the ALU inputs going to be for this project? It has X and Y, which are 16-bit inputs. So the ALU always is able to operate on two values. Okay. There are ways to get it to operate on only one value, but fundamentally it operates on two distinct values. Okay. So, what other inputs does it have? It has ZX and ZY. Now, what do these mean? These mean ignore X or Y and use 0 instead. So if I have the ZX bit at a 1, it means we're going to ignore whatever is coming in on the X bus and fill it in with 16 zeros. If ZY is set to 1, we're going to ignore whatever is coming in on the Y bus and fill it in with 16 zeros. Okay? So very, very important. Thinking about the circuits you're building in chapter 1, what kind of gate might you use in resolving what X is going to be, what Y is going to be in light of the existence of this ZX or this ZY? A multiplexer. Right, this is just screaming multiplexer, isn't it, right? What will be your, so you'd use like a MUX16, right? And the Z's would be what input for the MUX16? The select input. Interesting, right? So you're building multiplexers this week. For Wednesday, you are going to be multiplexer connoisseurs. You are going to be multiplexing like you've never multiplexed before. You'll be using them right and left. Multiplexers are a beautiful, beautiful technology for indicating how to switch between options at the circuit level. And you're going to be using them massively in your ALU. To the point where you're going to be like, if I didn't have these, I would have to invent them. And then I'll just say, that's why you did them in chapter 1. Okay, so the next inputs are NX and NY. So these stand for negate X or Y. Now, by negate, we mean not. Just invert the bits. We don't mean perform 2's complement. 2's complement will turn out to be an emergent property of several ALU operations working together. So not x, not y is negate x or y. Now something very important at this point is to think about, well, wait a minute. If I can zero it out and I can negate it, what happens if I do both things? So what do you all think the likely intent is here? You think the likely intent is if they're both set that you first negate it and then zero it out, or that you first zero it out and then negate it, producing a bunch of ones? What would be your guess as to the intent? So yeah, Andrew.
Since the zx and zy means ignore, I'll do that one second. Because if you set that one, that means that you want to ignore those values.
So let's walk through this. It's not just ignore, it's ignore and use zero. So let me rephrase the question. What would have more utility? Zeroing and then negating, or negating an arbitrary input and then zeroing? Yeah, Paxton.
Zeroing and negating, because if you want all zeros, you can just zero it. If you want all ones, you have to zero and then negate.
So that's the intent. And the way that we can understand that intent is it just creates more possibilities, right? If we negate first and then zero, then we have eliminated a possibility. By zeroing and then negating, we have a way to say load with zero, load with all ones. And that's going to create some other options down the road which are going to be useful. So the reason I'm going over this now is once you're in the weeds of creating the circuit, it's pretty easy to get yourself mixed up in, well, wait a minute, which one's supposed to go first? And of course, the book's truth table will make it very, very clear. That said, I think there's some value in trying to think about what would actually be the most useful way to interpret what they're telling us. And so in this case, that's the interpretation that I would want you to use. Okay, good. So you have nx, ny, zn, zy, blah, blah. Okay, so the next input is just called f. So what does f mean? 1 equals an add, 0 equals an and. So this is pretty interesting to think about. We can either be adding x and y, or we can be anding x and y. At its core, all the ALU ever does is to add two things or and two things. Of course, at some point, you'll be wondering, well, then how on earth is it going to or and everything like that? And we're going to go over that in a moment. But at its core, buried deep in it, there's going to be an add 16 and an and 16. And after all of this pre-processing, there will be some kind of circuit that picks between the two. What kind do you think that'll be again? A multiplexer, yeah. This looks freakishly like a select bit. Right. So the multiplexer is just going to pick between those two operations. That's the mathematical core of this ALU. We're not quite done. There's one more configuration bit, NO, and that is negate output. So those are all the inputs. X and Y, ZX, ZY, NX, NY, F, and NO. Just looking at them as a collection of labeled inputs and looking at the truth table, it's pretty easy to kind of get lost in the noise and just sort of be like, whoa, there's this crazy complicated thing that's got all this crap going in. That's not really what it is, right? Every single one of these inputs has a specific role and purpose in being involved in the ALU. And that specific role and purpose is something that, as you're designing the circuit, is a matter of keeping track of at each stage in which X and Y are flowing through the ALU, which version of them is the version that should be under consideration at each point. So the outputs then are as follows. There's going to be out, which of course is going to be a 16-bit output. And then there's going to be ZR and NG. ZR is a 1 if all 16 of those are a 0. Otherwise, it's a 0. NG is a 1 if it's negative. How do we know if our output is negative? Yeah, you check the leftmost bit. That's all there is. All 16 are 0. Well, let's just say or 8-way is going to have some utility there, for example. Okay, so that's the ALU in a nutshell. Let me nutshell it a little bit. There we go. So ALU in a nutshell. Of course, this is all given on pages 36 and 37 of your book, but it's worth working through what each of these aspects represents. To conclude our tour of the ALU, what I want to do is have us begin working through. I'm going to work on this a bit more on Tuesday as well. We're going to work through the implications of setting these bits in particular ways. We're going to go ahead and begin with the logical aspect. That is, let's imagine the operation we're performing is an AND. We're going to see how might we derive OR, for example, given an and how might not be derived using the ALU. So what we're going to be concerned with then is what configuration of these gets us where we want to go. So, and itself, of course, is very easy. We just say f equals 0, zx, zy, nx, ny. Those are all happily zeros, right? And we get an and. So now we want to think about how we can get an OR out of this. So there are a couple of aspects to thinking about how we derive such a thing, and I'm going to work through it with you all in terms of the truth tables. So I'm going to scoot over here and put together a little truth table. Okay. So when we examine the truth table, we can notice that to derive OR from an AND, they have a certain symmetry to them, right? AND is kicking out 3 zeros and a 1, OR is kicking out 1 0 and 3 1s. So what we can try to do is to think about negating an and then finding ways to rearrange the digits. Here's what I mean. Let's imagine negating A and B, okay? So that's NAND, of course. So I get 1, 1, 1, 0. So my goal now is to think about how can I rearrange things so that I get a 0 up here and a 1 down there. And that's where some of these other input bits come in handy, right? So notice I can negate the output. Somehow this must be an ingredient, right? I've got to be negating the output. because that gets me from 3 zeros and a 1 to 3 ones and a 0. My other resource is I can negate the inputs, right? So if I can negate the inputs, that creates some interesting possibilities. Consider this. What if I have not A and not B? Well, that'll give me a 1 here and then zeros all the way down here. And now what if I not A and not B? Then I get 0, 1, 1, 1. What do you know? That is the same thing as A or B. If I not A and not B and not it, I get A or B. So coming back here then, I can see, oh, if I want to do an OR, I set F to 0, I set NX to 1, NY to 1, NO to 1, and of course, ZX and ZY are both still at 0. I'm not zeroing anything. And what I hope this does is it illustrates the subtleties involved with this ALU design. That is, on one level, it's just like, what? I just get to pick between add and and? What kind of nut house ALU is this thing? I can't even OR. But it turns out, right, if I negate both the inputs and the outputs, my AND becomes an OR. So what about not? So let's imagine we're doing not. I'll set F to 0. And what I want to do then is I need to ignore one of my inputs, right? It doesn't really matter which input I ignore. So let's ignore Y. So if I'm going to ignore Y, I say ZY equals 1, and of course ZX is going to be 0. So I'm ignoring Y. What else do I need to do? I'm setting F to 0. I'm doing an AND. I used ZY, I set Y to 0. What else might I need to do at this stage to make my not work? Yeah, Andrew.
You need to negate X.
Okay. So I can set NX to 1. What else might I need to do?
That's a question.
Yeah.
I thought not always receives like one input.
What's that? Sorry?
And not always receive one input.
That's right.
Then opposite. In this case, are we still getting all these like 4 inputs?
So the ALU always receives 2 inputs because of its wiring. So there always have to be 2 things coming in. What we're starting to work towards here is to think about if I am implementing if I'm trying to create a machine language instruction that performs a not, which ultimately, of course, is exactly what we're doing, okay? So actually, once we work out the ALU bits, that's like half the bits in a machine language instruction. So part of the CPU's decoding process is it takes the 16-bit machine language instruction and it sends pieces of the bits of the instruction to different parts of the CPU. One big chunk goes straight to the ALU. So we want a not instruction in our machine language, is where we're going with this. So what will ultimately happen then is the inputs will just be wired in, but the machine language instruction will be defined to say only not a value coming from this direction. And then what we would do is we would set up the wiring to make it arbitrary, right? We could make it X or Y or whatever. So for now, we're just assuming it's X and Y is being ignored. So right now we've set ZY at 1, we've zeroed out Y. We've set zx to 0. We're keeping x. We've set nx to 1. We've negated x. And I'm wondering, do we need to do anything else? Yeah, Andrew.
Since we're using the and for f,
Mm-hmm.
do we need to negate y also?
And why would we want to do that, Andrew?
Because that'll make all the y's ones. So, and all like the zeros for the x's are ones now, and they'll be 1 if they're both 1 when you're adding them.
That is correct. Phrased slightly differently. By negating y, we make it all ones, and 1 is the identity element for the and operation. That is, whenever you and something with a 1, it just stays as whatever it was, right? So if we make y all ones, and we and all those ones with our negated x is preserved as it makes its way through the ALU. And at that point, of course, we can just set NO to 0. And we've got our negation. Note that it would work if we swapped these. So we could set NX to 0 and NO to 1, and it would also work. In other words, it doesn't really matter if we preserve the original and then negate it, or negate it and then preserve it. Same operation. That's okay. There's often more than one way to do something with the ALU. But part of the lesson here, right, is being able to examine a weird circuit like this ALU and to see how setting these input flags ultimately produces a targeted output. Needless to say, any CPU designer creating a specification for the CPU is going to have to design the ALU very, very carefully to ensure that all of the targeted operations for the machine language are readily computable by it. Cool. Have fun with Project 1. It's due tomorrow night. Like I said, I'll be around most of the day tomorrow. Today, I'll be around for a while in my office after this class and before my 2:45 class as well. So, got questions? Let me know. Have fun with it, and I'll see you all on Tuesday, if not before, in my office.